Welcome back to Multivariate Calculus. In this video, we're going to be looking at integrals in polar coordinates. We've seen previously that we can deal with iterated integrals in rectangular coordinates by setting up the infinitesimal area dA is equal to dy times dx, turning our expression into two simpler integrals. But when we're talking about regions in two-dimensional space, sometimes it's more convenient to describe those regions using polar coordinates. Let me get my head out of the way. Let's quickly review. We've done this several times. It shouldn't be new to you at this point. But if you are anything like me, thinking about polar coordinates is one of those things that you think about and then you don't think about for a while, and then you have to remind yourself every single time, up until you've been doing it for about 3 years, at which point it starts to become a little bit more natural. But polar coordinates, instead of being given an x and a y, you are given an r and a theta. R is measured as the distance radially out from the origin, and theta is the angle measured from the x-axis towards the y-axis. And for any region which is rotationally symmetric, or even just rotationally symmetric on some portion, polar coordinates can be a very effective way of describing it. And of course, we can always think about functions given f of r and theta instead of f of x and y. All right, so if we have some region, and I'm going to assume that our region is somewhat annular in shape, that is a disk that is hollowed in the middle, then we can think about some infinitesimally small bit of this, which I'm going to draw using some curves at an angle, which doesn't make sense at first glance, but as you think about it, it should make perfect sense because the radial coordinate r is measured in this direction, which means that this side and this side of the shape are infinitesimally small bits of our radius, dr. And then, of course, going in this direction follows along the curves of all of the circles that are defined by theta. Although it's not quite so simple as to say that this bit here is just theta, because that's not how distances work. But when you have a circle, that was the simplest version of arc length, where we got that the distance across a curve S is equal to r times theta. And when you are on a circle looking at arc length, r is constant. So some little tiny bit of that arc of a circle is going to be r times d theta. Finally, even though my region here has two curved sides to it, if I am looking at a small enough piece of that region, I can pretend that those sides are straight and get that this tiny little bit of area is essentially a rectangle, which has sides dr and r d theta. So all told, my dA is r dr d theta. And remembering that that r has to be there is going to be one of the big keys of keeping this straight. Right. Integrals in polar coordinates come up quite frequently in a lot of physics applications. especially anything that has to do with um, astronomy or any study of atomic or molecular physics, because those things tend to be rotationally symmetric. Anything that you study in either of those fields, so modeling them using polar coordinates tends to be a fairly reasonable thing to do. All right, let's start off with a relatively simple example. Let's say that I have some f of r and theta, which is given as r squared times the cosine of theta. And my region of integration is here in the first quadrant. It is, in fact, a bit of an annulus, right? A circle with a hole cut out of the center of it. These two rays are going to occur at pi over 12 and at 11 pi over 12. I'm sorry, I'm looking at the wrong problem. That's not the numbers I want here. I'm looking at pi over 6 and pi over 3. A later problem is going to have those other numbers, which we may or may not have time for in this video, depending on how fast I get through everything. And then my distances here are 1 and 5. And again, I am claiming that both of these curves are nice circles, so that tells us that staying in polar coordinates is going to be certainly the most convenient thing to do. And of course, this is the region that I care about, that is my R. So the double integral over this region of f of r and theta dA is going to be theta goes from pi over 6 to pi over 3. R goes from 1 to 5, r squared cosine theta, and then dA is r dr d theta. I'm not going to say that it never happens, but by and large, you will not find yourself wanting to use integration involving polar coordinates unless you have a case like this where r and theta both have constant limits of integration. When you have that as your setup, it tends to be that polar coordinates are easily the best choice. When you don't have that as your setup, it tends to be that you are just as well off using rectangular coordinates, unless you very specifically have a setup like we have in this problem, where the function is already given to you in polar coordinates. For this problem, I'm going to do something that I haven't done previously. Because r is completely independent of theta, right? My inside limit of integration does not have theta appearing in either the lower or upper limit of integration. Because of that, I can actually split this up. I can take all of my thetas, which are completely constant with respect to r, and I can bring them in front of that integral. Leaving behind just the integral from r equals 1 to 5. R squared times r is r cubed dr. And I get two completely separate integrals. Whenever you have constant limits of integration, this can happen. We did some problems that used rectangular coordinates and constant limits of integration, but the functions we were looking at weren't multiplication, they involved addition and subtraction. So this kind of an idea wasn't nearly so useful. But in this particular case, because our function involves multiplication and our limits are all constant, we can split this up. It makes doing the next several steps of work quite a bit easier because we can do both integrals in a single step. The integral of cosine is, of course, sine. The integral of r cubed is 1/4 r to the fourth. And then we just evaluate. Sine of pi over 3 is the square root of 3 over 2. Sine of pi over 6 is 1/2. 1/4 times 5 to the fourth power is 625 over 4. And 1/4 times 1 is just 1/4. So we've got square root of 3 minus 1 all over 2 times 624 over 4. 624 is definitely divisible by 4. My calculator tried to run off on me. Let's see. 624 divided by 4 is 156. That's still even, so that's actually still divisible by 2. So 624 over 4 and over 2, all told, is 78. And then we have left square root of 3 minus 1. So 78 root 3 minus 78. Or you could get a decimal approximation if you would like. Square root of 3 is something like 1.76. Subtract 1, that's 0.76. Multiply that times 78, and you will get something in the ballpark of 19, 18, somewhere thereabouts. Good enough. As I said previously, when you have a function that is given in polar coordinates, that makes your life a lot easier, but very often you have a function that is not given in polar coordinates. And yet, when you look at your limits of integration, you find that it might make a little bit more sense to describe your region using polar coordinates. All right, so here we have a region. Our function is given as f of x and y. Our region is here in the second and third quadrant, and it's part of an annulus. It's a circle with a circle cut out of the middle of it. And we could set this up integrating with respect to x. We realize we have to break this into 3 separate regions where things change. Integrating with respect to y, we again find that we have to break this into 3 separate regions where things change between them. But because it is rotationally symmetric, from theta equals pi over 2 to theta equals 3 pi over 2, my inclination is to try to rewrite this as a function of r and theta. X is r times the cosine of theta. Y is r times the sine of theta. X squared plus y squared is r squared. And so we're looking at the region r goes from 1 to 2. Theta goes from pi over 2 to 3 pi over 2 of this function r cosine theta plus r sine theta. And again, remember that dA in polar coordinates is r, dr d theta. That extra factor of r is important and is really easy to forget. All right, that gives us something to work with. Um, you can, in fact, factor out the r once again. And realize that in your inner integral, theta is constant. And because theta is constant, you can factor out anything involving theta from that inner integral, which allows you to split this thing up into two separate integrals. Oh, my pen and my brain are not connected today. I apologize. All right, so we look at the integral from pi over 2 to 3 pi over 2 of cosine theta plus sine theta d theta, and we multiply that times the integral. R goes from 1 to 2 of r squared dr. All right, integral of cosine is sine. Integral of sine is minus cosine. Integral of r squared is 1/3 r cubed. And then we evaluate. Sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Minus a minus is plus in there. 2 cubed is 8. So we have 8/3 minus 1/3 over here. It looks like we get -2 times 7/3, which is just -14/3. I've got one more example that I'd like to show you today. This is perhaps my favorite trick using area integrals and polar coordinates. The integral from generically a to b of e to the minus x squared dx. This is called the Gaussian integral after Carl Friedrich Gauss, of whom quite a few things are named. Generally, you most likely have seen the name Carl Friedrich Gauss in a physics course talking about electricity and magnetism. The Gauss is one of the most common units used for the strength of a magnetic field. So there's kind of a insight into some of the things he was involved in. But the Gaussian integral has nothing to do with that. The Gaussian integral is a key feature of statistics. Carl Friedrich Gauss came up with this mathematical function to describe the normal curve, or the standard bell curve that you see in population distributions, with that peak at the center and tapering off quickly on either side. If you put some coefficients in front of this, and this is a calculus class, not a statistics class, so I don't care about the coefficient that goes in front, and you calculate an integral from a to b, the result actually turns out to be the probability that a randomly selected sample from a normally distributed distribution falls into that region. Key features of this sort of thing ask questions like, what is the probability if you select a person at random that they have an IQ somewhere between 95 and 115? Knowing that IQ scores are normally distributed and going from there. Again, that's getting into the statistics of it. I don't care about that. I will mention that this is something that is actually well known. If you take a course in statistics, you are handed a table where somebody has done this integral for you for basically every interval that might matter, and you can do some algebra and geometry tricks to figure out how to get your number off of that table. But it is possible to do by hand, although it's very difficult. At this point, I should probably address the fact that this is not an area integral by any means whatsoever. This is a normal integral of a function of one variable. But it has a bit of a problem. If you try doing a use substitution, you get that du has to be minus 2x dx, and there's not an extra x laying around anywhere. And the reason that I like showing this integral is because the creativity of coming up with this trick is just absolutely mind-blowing to me. Let's call this integral I. And here's the start of a trick that we've used a couple of times in previous coursework. When we don't know an integral, we call it I, we do some algebra to it, and we see if we can turn that into something that we can actually solve. The algebra we're going to do to it this time is, it turns out that I is too challenging to figure out. So what if instead of I calculated I squared? Well, I squared is the integral from a to b of e to the minus x squared dx multiplied by the integral from a to b of e to the minus x squared dx. Now, when you're doing a definite integral, the variable that you're integrating over is what we call a dummy variable. When you have finished performing the integration, it's no longer going to be appearing in the expression anywhere. And so it's perfectly reasonable to use any variable you'd like. When we were looking at the fundamental theorem of calculus in Calc 1, we very often switched between x and t when we had a variable in one of our limits of integration. It's the same idea here. And so I'm going to change my limits of integration, or change my description of the integral. Instead of using x, I'm going to use y. And now I can't imagine why I would want to do that, but I can take this integral and I can bring it inside of that integral. It'll make things a little bit messier. And I'm going to get the integral x goes from a to b times the integral y goes from a to b of e to the minus x squared times e to the minus y squared dy dx. All right, just cleaning this up a little bit. Properties of exponents. Combining or multiplying like bases, you add the exponents. So e to the minus x squared times e to the minus y squared is e to the minus x squared plus minus y squared, and I just factor the minus out for convenience. Then going backwards of how we've done before, dy dx is just dA. And now we start to notice, wait a second here, I have an x squared plus y squared. That's the same thing as r squared. I can change this into polar coordinates, and then my dA is r dr d theta. And because I have this extra r here, I get e to the u du d theta. And I have this separated where I can do things separately. Integral of d theta is theta. Integral of e to the u du is e to the u. And then my limits of integration are not something that I've noticed so far, but I can make things work. I claim that I can just set up this limit like that. Going back and thinking about this, it gives me a small window here. And so I'm looking at a slightly different problem here with my limits of integration, but I can make it work out. Very specifically, a place where this gets used often, we're going to send A to negative infinity, send B to positive infinity. And instead of trying to look in a finite region, let's look at the entire thing. This is the trick that's used to figure out what that coefficient has to be. And once I've done that, then instead of, if I can use the right button, sorry about that, instead of having this square region, I'm now looking at the entire plane and the entire plane. Well, that's r going from 0 to infinity, or u going from 0 to infinity. I'm sorry, that's r going from 0 to infinity, which means that u itself is going from negative infinity to 0. And then my radial direction, I want the whole thing, that's 0 to 2 pi. All right, so it doesn't work in general, but it works in this one case. A goes to negative infinity, B goes to positive infinity. And that's going to be r from 0 to infinity. And again, since u is minus r squared, that's why u is going to go from minus infinity to 0. So we get 2 pi. E to the 0 is 1, e to the minus infinity is 0. So we get 2 pi, we get a 1/2, and we end up with pi as our result there. All right, so a fun little trick out of statistics that I like showing and playing around with. For one thing, it is a trick that we can use um, because actually I jumped in earlier. There's still one more step because this is I squared. I itself is going to be the square root of pi. And if you've studied statistics, if you've looked at the normal distribution and you've ever seen the equation for calculating it, which again is normally done numerically, you'll find that there's a 1 over square root of pi that shows up. Why does pi show up in statistics? Well, because of this. So it's something interesting that you wouldn't think of. It's a really nifty problem-solving strategy when it comes to trying to perform integrals that's a little bit of outside the box thinking, and that's why I like talking about it. All right, but I would like you to look at something a little bit simpler than this. So let's clear that off the screen and let's look at one more example. Right? F of x and y is equal to x minus y see if I can actually draw this reasonably well. All right, so we've got a couple of lines that I've drawn in here. X equals y, x equals the opposite of y, x squared plus y squared equals 4, and x squared plus y squared equals 25. And if you look at where all of these regions overlap, you get this region right in here that I'm interested in. I'm going to call that R, and we're looking for the integral of over R of f of x and y dA. It shouldn't surprise you, this being the video on integrals in polar coordinates, but I'll give you the strong hint that you probably want to rewrite this in polar coordinates before figuring it out. I'd like you to take a few minutes, see what you can do with this one, and I'll see you in the next video.